Okay, today we're going to be talking about some nuclear chemistry, and we're going to be going over isotopes, nuclear structure, radioactivity, nuclear decay, and half-life. There's some references to nuclear power in here, but that's not going to be a main topic that's discussed. So before we do anything else, let's just make sure we know how to pronounce this word right here, nuclear. It is written as N-U-C-L-E-A-R, nuclear. It is not nuclear. It's not nuclear. It's written as nuclear. Nuclear is how it's pronounced, not nuclear. Before we go any further, just want to make sure we know how to pronounce that. It's a little bit of a talking point that I sometimes want to clarify. Let's get started here. So we're going to start off here just doing a little review of the atomic structure. We should all know how this works at this point. So it says atoms are composed of two fundamental sections. You have the nucleus containing protons and neutrons, whose number of protons dictate the atomic identity. So if something has 3 protons here, doesn't matter how many neutrons it has, it's going to be lithium here because 3 is the number of protons to determine the atom's identity. And then we have the electron cloud, which is the region around the atom where the electrons can be at any given moment. It's really a probability. It's probabilistic entirely. It's governed by the Schrödinger equation, and those electrons are going to be lost or gained depending on where the atom is on the periodic table to form ions. And the periodic table as of 2022 right now has 118 elements cataloged in it. Each element has its own unique properties, and that's going to be a result of the atom's rich electronic structure. The electrostatic things going on in the atom are really going to be what's controlling those properties. And atoms are absolutely modular. They can form molecules, formula units, alloys, etc., whatever, with other atoms. And they act as the building blocks of nearly everything physical. And another thing that's important to note is atoms are their own composite physical systems. Their electron clouds and nuclei have their own complex dynamics right here, or down here now. Extranuclear electronic activity. So that means everything outside of the nucleus is going to be described by the Schrödinger equation we talked about, the electrons. And then the nucleus is described by nuclear and particle physics. Like a little cool thing to note here, the math and science and physics that describes the nucleus, and particularly the interactions inside it, is called quantum chromodynamics. Quantum chromodynamics, or it's usually abbreviated as QCD. These are the same thing, and that just describes the nucleus and things largely that go on inside it. And the Schrödinger equation is quantum mechanics. And that's usually just QM. You'll see it sometimes written the same thing. And here's just a little picture to show the structure of the atom here. Of course, we have the nucleus, we have the electron regions around it. Obviously, these electron orbitals, these shells, are not going to be ellipses around the nucleus. They're going to be 3D shapes, determined again by the Schrödinger equation over here. This is just a handy Bohr model representation. And we notice that we have an average atomic mass here. This is an average atomic mass of 6.94. In the nucleus, we have 4 protons and 3 protons. That's going to be 7. So this is going to be lithium 7, but we do average atomic masses, and when we write this, we just round this to the nearest whole number. But we do average atomic masses on the periodic table, and that is why it's 6.94 with an uncertainty here, and that's why it's slightly different than this over here, because obviously you can't have 0.94 of a neutron, but that's all that means. So we were just talking about average atomic mass, and we're going to get to why that's important and why we have to do that right now. And that's because atoms are going to have different isotopes. Every atom is going to have multiple isotopes of itself. And so the slide says the mass of an atom is equal to the sum masses of its protons and neutrons. This mass largely comes from the nuclear binding energy in the nucleus. We'll get to the nuclear binding energy in the nucleus here in a little bit, but for now all we're looking at is the idea that atoms have different isotopes. So the same atom, they just have different numbers of neutrons, different weights, different masses. An atom's identity rests with the number of protons in its nucleus, but different atoms of the same element can have different numbers of neutrons in their nuclei, meaning they will have different masses, and that's something we just said. And the periodic table displays the weighted average atomic mass for elements. It is calculated from the sum of a given isotope's mass multiplied by its relative percent abundance, and then we have this LaTeX equation down here that I put in. The relative percent abundance of a given isotope is a decimal form of its percentage value. So to get that, we just take the percentage and we divide it by 100, and then that is our decimal value of our percentage, and we use that for our calculation. So let's run through what this means here. This equation, a little bit of some notation I put in LaTeX. So the average atomic mass, we'll write it like this. average atomic mass is going to be equal to the mass of isotope 1 and the percent abundance of isotope 1 plus the mass of isotope 2 multiplied by the abundance of isotope 2 plus dot 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 for every one of the isotopes. And then the average, our weighted average, is going to be the average atomic mass. That's all that this is. This is just a more formal way of writing it, I suppose. And then our picture here, we have the isotopes of hydrogen. We have protium, deuterium, and tritium. And that's why the hydrogen isn't just 1 or 2. It's not a flat number for its atomic mass here. Obviously it's got 1 proton, and that's reflected in all of these, but these have varying numbers of neutrons in their nucleus. So when we do the average atomic mass here, we take the percent abundances of these, this, and this. We do it in this equation here. This is the number we're going to get, with some uncertainty, of course. So now that we've discussed how average atomic mass is calculated, we're going to do a practice problem just to make sure we understand it. So the question reads, determine the average atomic mass from the data provided. Using the atomic average, identify the element whose isotopes are listed in the chart. Then identify the isotopes. So we're going to have to do our formula here, so let's write it down in a way to remember. So average atomic mass is going to be equal to the mass of 1, or the abundance of 1, plus mass of 2, abundance of 2, plus dot dot dot. So this is our equation here. So we have 3 isotopes here we're going to have to do this for. So average atomic mass, we're just going to do this as this vinculum over the m, that just means average, so m bar, going to equal the atomic mass of 23.98504 multiplied by 78.7 divided by 100, which is just 0.787, plus 24.98584 multiplied by 0.1013. And then we're going to add the last term here is just going to be 25.98259 multiplied by 0.1117. And we put this in our calculator. Let's do this really quick here. Get 23.98504 times 0.787 plus 24.98584 times 0.1013 plus 25.98259 times 0.1117. We get that, we're going to get an average atomic mass. We're going to round to 3 significant figures because that's what we have up here, of 24.3 AMU. This is our average atomic mass. Let's make sure we put a unit on that. AMU, or you could just do U there. It's the same thing here. Circle this here. And now we have to identify the element. So if we look at our periodic table, what element is going to be closest to this? So if we look at our periodic table, we're going to see that this element is most likely going to be magnesium, Mg. That means these are the isotopes of magnesium that we've just found. And now we need to do the last part of the question, which is just identify the isotopes. So isotope 1 is going to be magnesium 23, about 24. We're going to round this to the nearest whole number, so it's going to be 24. And magnesium has a number of 12, atomic number of 12. It's going to be isotope 1. Isotope 2 is going to be magnesium, round to the nearest whole number, 25. And of course 12, we don't always have to put the 12 there. We'll go over notation in a little bit. And the last isotope is going to be magnesium 26, 12 there. So these are our isotopes, and this is this practice problem completed. So our element was magnesium, and we just found the average atomic mass to prove that, and these are the isotopes of that element. On the topic of isotopes, we're going to be looking at isotopic stability. And obviously, when looking at isotopes, they're going to have varying masses. The different masses of these isotopes have an effect on their stability. These isotopes have different ratios of neutrons to protons in their nuclei, and that makes sense. Maybe one isotope of lithium is going to have 3 neutrons and 3 protons for a mass number of 6. Maybe another one's going to have 3 protons and 4 neutrons with a mass number of 7. They're just going to have different ratios of protons to neutrons. And this over here is the band of stability. It's also going to be called the island of stability, and it's going to map the ratios of protons and neutrons and atomic nuclei to visibly represent a region of stable nuclear ratios. And when I say stable, I mean not radioactive. And on here we're going to see the black here is going to be the stable atomic nuclei, and everything else, we'll get to what these mean up here, but it's going to be unstable if it does that, anything else. And generally speaking, the heavier an isotope is, the more unstable it's going to be for a given element. And that's just intuition. If the ratio is bigger, we can see on this chart it's going to be more unstable. The band of stability is experimentally determined. There is not a sound theoretical way to determine nuclear stability without aid of experimental data. Of course, we're not going to get into the more advanced mathematics of nuclear physics or quantum chromodynamics here, but there are some ways where you can maybe get some idea of what's going to happen, but you have to determine the reality of things experimentally using particle colliders and such. And elements past a certain threshold become intrinsically unstable and decay very quickly. To be considered an element, a nucleus must remain unchanged for a set period of time. And this is why we don't have a bajillion elements, right? Because we can smash together in a particle accelerator, because that's how these things are made usually past a certain point. We can smash together two things, and maybe they'll stick together for the tiniest amount of time. But just because they stuck together and made another nuclei before they destroyed each other, that doesn't mean that it's going to be considered an element. So element 118, oganesson, is going to be the most recent example of this. And so before continuing any further into our topic here, it's going to be prudent to understand nuclear and subnuclear structures. So I just have some vocabulary terms and some structural stuff to know about the nucleus and what goes on inside it, so we can understand this before we go any further. So the first thing here, the atomic nucleus, is a nuclide made of nucleons held together by the strong nuclear force. A nuclide is a structure of nucleons, and nucleons are protons and neutrons. So just these first three, let's unpack these first three for a second. What did we learn here? We know that the atomic nucleus is an example of something called a nuclide, and it's held together by the strong nuclear force, which we will discuss in a second here. A nuclide is a structure then of nucleons, and nucleons are protons and neutrons. And in fact, nucleon is the umbrella term for proton and neutron. In fact, it's a superposition of the two. Protons and neutrons are the two states of the nucleon. We'll get to that in a second. But this is like the core thing to keep in mind when looking at the atomic nucleus. And then the next thing is going to say protons and neutrons. And like we just talked about, they're the two states of the nucleon. And they are not fundamental. Protons and neutrons are not as fundamental as it gets. They're going to be composite structures made of quarks, specifically up and down quarks we'll discuss in a second. And they are examples of hadrons, or hadrons, however you want to say that. Hadrons are just a term for a composition of two or more quarks bound by gluons of the strong force. So let's look at this second part here. We learned that protons and neutrons, just like a second ago, are the two states of the nucleon. And protons and neutrons are in fact made of other smaller, more fundamental particles called quarks. They're made of up and down quarks, protons and neutrons are. And they're examples of hadrons. And hadrons are just two or more quarks that are stuck together by the thing called the strong force, by the gluons. Now protons are going to be made of varying ratios, protons and neutrons of up and down quarks. So a proton, we'll get to this more on the next slide here, but a proton is going to have 3 quarks, is going to have 2 up quarks and a down quark. This is going to be a proton. Then a neutron is going to be an up quark and 2 down quarks. We'll get to why this works on the next slide, but just know that this is a proton, 2 up quarks and a down quark. A neutron is 2 down quarks and an up quark, and these are just examples of hadrons because there are 2 or more quarks here. There's 3, so that makes them a hadron. Quarks then are a classification of fundamental fermions, and fermions are a classification of particles on the standard model of particle physics, and they represent all the physical stuff, all the matter everywhere. And there are 6 types of quarks. There's ups and downs, which are what's inside here. The up, the U is for the up, the D is for the down here. That's just inside protons and neutrons. There are charm quarks, there are strange quarks, there are top quarks, there are bottom quarks. Fun fact, the top quark is the heaviest quark of all of them that we know. And gluons, mentioned up here with the strong force, are the gauge boson, and that just means it's a force-carrying particle. It's not physical in the same way that a quark is that makes up a proton or an electron is that's around the atom. It's just going to be a force representative, and that's what it's a gauge boson. That's what that means, of the strong interaction. And we saw the strong interaction up here, it's the same thing as the strong force. We're going to get to that here. But first thing we need to talk about is the strong nuclear force, which is what holds together, remember, the atomic nucleus up here, the strong nuclear force. And it's going to be the force obviously binding the atomic nuclei together. It importantly is strong enough to overcome the electromagnetic force that would have protons and neutrons repel each other. So let's think about that part for a second. So like charges are going to repel, opposite charges are going to attract. That's Coulomb's law right there. That's basic electricity and magnetism. But why do a positive charge and a neutral charge stay together? Why is that? Why don't they repel each other? Well, in an instance like the atomic nuclei, a nuclide, we see that the strong nuclear force is there, and that's going to be the leftover, quote-unquote, leftover remnants of the strong interaction that we see inside of hadrons here. And it's going to be mediated by the exchange of pions, and pions are just different ratios of a top quark, or excuse me, a down quark or an up quark, of antimatter quark or normal quark together, and there's two of them in there, so they're also a hadron. They're actually classified as a meson, M-E-S-O-N. But that's a bit technical, we're not going to get too far into that. The strong force, which the strong nuclear force is a derivative of, think of it that way, the strong force is also called the strong interaction, and it is one of the four fundamental forces. The strong force is going to be mediated by the gluons up here that we talked about between quarks, and this is the study of the strong force is going to be quantum chromodynamics. That's what that's going to be right here, the strong force. Nuclear physics is going to be more the study of the strong nuclear force, and quantum chromodynamics is going to bleed into that maybe, but mostly that's the study of the strong interaction. And the weak force, just something to know, is called the weak interaction. It's another one of the four fundamental forces. It's going to be mediated by the W and Z bosons. There's 3 of them in total. It's going to be associated with nuclear decay. And this is less important, but the main things we need to look at are the strong force and the strong nuclear force. So what did we learn? We learned that the atomic nucleus is made up of nucleons, or protons and neutrons. It's bound together by the strong nuclear force. Now the nuclear force is in there to signify that it deals with the nucleus. Strong nuclear force deals with the nucleus. That's why nucleus is in there. That's what nuclear means. It means pertaining to the atomic nucleus in this instance. The strong force without nuclear is going to be the underlying fundamental force. It's going to be mediated by gluons between quarks. That's what's going to bind together hadrons and protons and neutrons and everything. The strong nuclear force is again just going to be pions, which are mesons. They're made of quarks just like protons and neutrons, except they're a different ratio of different types of quarks. And the weak force is again less important here, but we'll get to it when we get to radioactive decay. It's another one of the 4 fundamental forces. So the 4 fundamental forces for reference are the strong force, the weak force, gravity is one, and then the third one is the electromagnetic force that we saw up here. Gravity is not relevant on a quantum scale like this, but it's just a little reference there so you can know all 4 fundamental forces. So this is just to make sure we understand some of the terms, and so we understand some of the structure of the nucleus and subnuclear world, just to make sure we don't get confused, because the understanding of quarks and how they can change is going to be really important going forward when we look at things we're going to talk about next. And here, this is sort of like a continuation of the last slide. I just made it a little bit more visual so we can understand what's going on. So we're going to start over here with our atomic nuclei here with the strong nuclear force. Remember, not the strong force, it's the strong nuclear force here. So an important thing to know, like a little fact to know about the atomic nucleus, it's not a static structure, right? These nucleons in between, they can move around, and they in fact have energy levels just like electrons or similar to electrons in shorting or orbitals and shells around it. And remember, nucleons are a superposition between protons and neutrons, so these can change at any given moment, but it always, for an atom to have one identity, is going to have the same number of protons, maybe with varying number of neutrons in each of its isotopes. So let's look at this. So we have the strong nuclear force being indicated here between protons in red and neutrons in blue. And I've got these green boxes around the arrows, because that's going to be the strong nuclear force. And if we look to where the other green box is over here, we're going to see the pions. And this is going to be really important, because these are the 2 that's going to be really important in mediating the strong nuclear force, the positive pion and the negative pion. And we'll get to these numbers down here for a second once we go through everything, but I did want to point that out. These are pion exchanges here between the nucleons. Then if we continue to protons and neutrons, again the proton is boxed in red here, neutron is boxed in blue. We see the protons do indeed have a ratio of 2 up quarks to 1 down quark, and a neutron is the opposite, it's 2 down quarks to 1 up quark. And the up quarks here are in this sort of hot pink color on here, so this is the up quark. This is what the U is for. The down quarks here are in this darker pink color, maybe almost purple. The down, that's what that's for. And then I have this orange box around these slinky looking things in the middle. What are those? Well, those are going to be our gluons. Remember the gluons, we can represent this as G like it's in the box up here. The gluons are going to be the quanta, the gauge boson of the strong force, strong interaction, not the strong nuclear force, just the strong interaction. So the orange boxes will draw a thing here. It's going to be the strong force. And it's aptly named because the strong force is actually the strongest of the 4 fundamental forces. It's so strong that when these quarks move around and they go too far from the other ones, the gluons pull them right back. And if they go too far, a quark-antiquark meson pair is created. And that, remember, mesons, these pions, look at these quark-antiquark. The bar above a quark number, so if I did this, that's an anti-quark, that's an anti-up quark. If I do a normal D, that's a normal down quark, but if I do that, it's an anti-quark. And anti-quarks are just the antimatter counterparts of quarks. But if it goes too far, the strong force is going to pull it back. And if it goes too far, it's going to create one of these mesons over here, one of these pions. And that's the structure. But I do want to look at charges and spin. So charges in this yellow box here, we're going to look at up quarks. If we have an up quark, let me erase this here for a second. If we have an up quark here, it's going to have a charge of positive 2/3. And if I have a down quark, it's going to have a charge of negative 1/3. And the charge here system is just, again, a derivative of an electron having a negative 1 charge, proton having positive 1, so we make the charges of these line up, and that's how it carried over. So if we have a charge of an up quark, it's going to be positive 2/3. We'll put an E here. The down quark is negative 1/3 E. So demonstrated down here, if we have a proton, if we have 2 up quarks and 1 down quark, if we use our calculator, 2/3 plus 2/3 minus 1/3 is going to be equal 1 charge, and that is why protons have a charge of 1. Same deal over here with the neutron. If we have 1 2/3 minus 1/3 minus 1/3, that's going to get 0, and that's why your charges are the way they are. Same thing with the pions over here. A pion is going to be indicated as charged with a plus or minus superscript. Same thing over here, but that's not too important for what we're doing. So just for now, understand that pions are the exchange of the strong nuclear force that they're mediated by. The other thing that's unique about quarks that I want to look at and gluons is that quantum chromodynamics, let's write this out again, QCD, quantum chromo. So what does chromo mean? Chromo is, I believe it's Greek or Latin for. Chromo is, let's move this for a second, chromo is going to be color. Chromo means color, and in fact, in QCD, we do have a color system. It's not like colors you think about now, but see, this is a blue, this is a green, this is a red, this is a green, this is a blue, this is red. These have colors also, and anti-colors are associated with antiquarks here, or they can be, rather. That's called a symmetry of the strong force, but that's not something that's really technical. We're not going to be looking at that, but that is a unique thing to understand about gluons and quarks. It's a very complex system. It doesn't really translate into the strong nuclear force, so as far as nuclear chemistry goes, that's a bit obsolete, but just understanding the structure of how the subnuclear world works is really important. So again, this is just a visual representation of some of the particles at play here, some of the exchange particles, some of the quarks here that's going on, the gluons and everything to make sure. So we start at this fundamental level, and these are the same picture here. This one just elaborates on charges and spin. We're not worried too much about spin. It's the same spin that you see in electron moments. It's a quantum effect that we interpret relativistically, but it's not really important for nuclear chemistry. But these are the same pictures. So we know that the proton has a charge of positive 1 because it has a ratio, a certain ratio of ups and down quarks that have their charges add up to positive 1. Neutron has a charge of 0 to electrically neutral because it has the ratio between down and up quarks that give it a charge of 0 E here. These things are bound together by gluons, which do not have a charge. They in fact don't have mass, but they have a spin of 1. Remember, spin is something, it's a quantum effect. We don't really talk about that in nuclear chemistry. And then these two, when they get together, let's say this is a hydrogen isotope, just a proton and a neutron, it's going to have an electron somewhere outside of it, are going to be held together by the strong nuclear force up here. And that's going to be mediated by these two pions here. These pions, depending on the nucleon, are going to be exchanged between these to hold the nucleus together of that said hydrogen isotope. And then that's how all atomic nuclei are formed, are just different ratios of ups and down quarks. To form protons and neutrons. Those protons and neutrons, those nucleons, are then bound together by the strong nuclear force, which is just pion exchange. And that's our visual representation of nuclear and subnuclear structure here. So now we're going to be starting our discussion about radioactivity and nuclear decay. So we're going to read what the slide says here. As shown on the band of stability, remember that's our chart of stable nuclear ratios between neutrons and protons. Most elements have radioactive isotopes in addition to stable isotopes. However, every element past lead, which is Pb on the periodic table, then lead's number is going to be 82. Every element past lead on the periodic table are intrinsically radioactive in every one of their isotopes. This is why neutron-rich lead is good radiation protection. So let's put that in layman's terms here. So everything with more than 82 protons in its nucleus, everything past lead, everything past that is going to be radioactive. If we draw a little radioactive symbol here, it's not a very good thing, but everything past lead is going to be radioactive. That's because it's going to be an unstable. It's always going to have an unstable arrangement of protons and neutrons in its nucleus, and that is what this first part is saying. And this is why lead, being neutron-rich, especially neutron-rich isotopes of lead, are good radiation protection. When isotopes of an element become unstable, they become radioactive. Radioactivity is a property exhibited by unstable nuclei when they undergo nuclear change. So radioactivity is just when a nucleus is unstable, it's going to change itself by ejecting particles or energy or whatever to try and approach a more stable state. When an element is radioactive, its nucleus is decaying or reacting in some way to approach a more stable state in mass or energy. Mass or energy, that's very important. And that's what these two are synonymous with each other. This is just an elaboration on this part up here. When a nucleus decays, it can eject particles and or energy, and these emissions are released at a very high velocity and with much energy. And that's actually how nuclear fission works for power. And on the topic of fission, this is going to be when a parent nucleus breaks apart or ejects parts. Two daughter nuclei are created, or two particles are created in fission. And this is again how most nuclear power is generated here on Earth. And this is an example of fission in a chain reaction here. Of course, there's something that happens in this already unstable uranium-235 nucleus. Neutron gets thrown at it, bam, it explodes. Some energy is released. Some more neutrons are going to be released. It's going to hit other uranium-235 nuclei. They're going to split into these krypton-92 and barium-144 nuclei, and that's going to be this chain reaction here. That's going to be what's going on in this nuclear power plant here. It's going to be happening in this reaction here. There's going to be control rods to make sure it doesn't get out of hand. Pump is going to carry this to a steam generator. There's going to be water in here. Then it creates steam. That steam is going to be turned to a turbine that turns to an electrical generator. That electrical generator is, of course, going to be turned to the switchyard where the power lines are. The water is going to be over here to cool in the reservoir, and it's a continuous cycle. Most of this power is going to be fission. There are some fusion power plants, like HB11 is an example of fusion. If you're interested in looking that up, it's very interesting. I'd highly recommend reading into it. But that's going to be the minority of nuclear power. Most of nuclear power is going to be fission and this chain reaction method using uranium or other radioactive elements. And then on the flip side of things, we're going to be looking at fusion. Fusion is when nuclei fuse together. This is really only going to happen in extreme conditions, and it happens in normal stars like our sun here to form heavier elements, so elements like iron and that sort of thing. Not like hydrogen. Hydrogen, helium, of course, are going to be in the sun, but through fusion you're going to get heavier elements like iron and whatnot. Again, HB11 is also going to be fusion down here, except this is on Earth, of course, and not in the sun. This is an energy project on Earth. This is in the sun. I do want to clarify here, extreme conditions, yes, in normal stars. That means it's not going to be in neutron stars, which are a special type of star. It's a little bit technical to get into here, but that's not going to be a thing, because in neutron stars, all of the electrons around the nuclei are going to be forced into the nuclei. It's going to turn everything into neutron. That compactification is going to continue. We don't really know what happens in the center of neutron stars, but we know that there's this material called nuclear pasta that probably forms. That's going to be very, very resilient. There are also quark stars, strange quark stars, which, remember, strange is another one of our 6 quark types on the standard model. Those are extremely enigmatic. So remember, as far as nuclear fusion goes, normal stars, where these nuclei under great pressure, great conditions, temperature and pressure, can fuse together to form heavier nucleus. So here, if these are our protons here in red, see we have 2 isotopes of helium, or rather, why don't we do this? Why don't we make our isotopes? When we make these our protons, so we have an isotope of hydrogen. We have hydrogen 3 here, tritium. We have helium 4, which we'll get to understand in a second. As an alpha particle of this nucleus, helium 4 are going to form this element. This is going to be beryllium, beryllium 7, because we have, or not beryllium, excuse me, lithium, lithium 7, because 3 protons, 4 neutrons are going to be lithium 7. And this is fusion when 2 elements, 2 nuclei of 2 different elements fuse together. It usually happens in stars. So before we go any further, we're just going to go over some quick notation here. You've probably seen me write things like this before, where we got an element here, we have some number up here, we have the proton number down here, and this is just going to be an example of standard nuclear notation. So when we write like if we want to identify an isotope here, we can put the name, like on the last slide we had lithium, put the element symbol here, we'll put the mass number above. So lithium 7 is going to have 3 protons and 4 neutrons, so total number is 7. Each proton, each neutron is 1 mass unit, so it's going to be 7. And then sometimes we're going to see the atomic number down here. Now, because we already have lithium here, this may be a little bit redundant sometimes. So if we're just trying to get things done quickly, we can also write just lithium 7, and these are going to be the same thing as each other. This 3 doesn't have to be here. It's sort of like a ghost, because it's understood that there's a 3 there because it is lithium, because the number of protons determines elemental identity. So if I wanted to write uranium 235, so uranium 235, and this is another example of notation here. We just have the element name, a dash, and then its mass number, so that's the total number of protons and neutrons there. We can write this as U 235, and then uranium's number is going to be 92 protons in the nucleus, and this is going to be the same thing as, of course, just 235. Let's write that a bit clearer. 235 uranium, because this number is understood to be there because it is a number of protons, automatically makes it uranium. So this is just a quick notation clarification here. We're going to see this a lot moving forward, especially when we get to nuclear equations. So if I wanted to write the isotope of a fictitious element X, let's say it has 119 protons. That's not been a thing yet. So let's say we want to write X, I don't know, X300, just a fictitious element. So if we want to write X, we'll call it xenonium, I don't know, xenonium 300, and this is element, let's say this is element 219. We're going to write this as, let's make its symbol what's not taken. Why don't we just call this Zn? Say this is the element symbol. Remember, it's made up, so it's 300. We can put 219 down here if we want to, but we don't have to. We can also write this as 300 Zn. So this works for any element, any isotope of any element. Probably this wasn't the best example to do a fictitious element here, but as long as we understand that some isotope, so element name here, put this in brackets, dash, we'll do mass number is going to be the same thing as element symbol, so we'll just call this element E, and then we'll put the mass number up here, and then the atomic number down here. this is really what we're going to get at. So we need to know these two types of notation, very common in nuclear chemistry and anything you do with the nucleus. So these are just two things to know. Notation clarification, we need this to move forward. I just thought I'd put this in here. So now that we've discussed the different notation that we can use in nuclear equations to represent isotopes and whatnot, we're going to look at a couple different modes of radioactivity and nuclear decay. Now, just something to go in here knowing, this is obviously not all of them. There are many, many more decay modes than these, but these are the most common ones, and are the ones that I feel like we should understand to get a good idea of how the nucleus works when it changes because it's unstable. So the first one we're going to look at, and we're going to elaborate on all of these with different slides in a second, is alpha decay. Alpha decay is classified as the emission of an alpha particle. We denote an alpha particle with just the Greek letter alpha. We can put 4/2 here because the alpha particle is defined as the nucleus of a helium-4 isotope. So obviously helium is the second element, so number of protons is 2, isotope is 4, helium-4. This is going to be the same thing as 4/2 helium, and I do have that in parentheses down here. These are the same things. And alpha decay is also going to release energy. All of these are going to release energy in some form or another. We have energy here. It's a bit ambiguous because it can be different things. We'll just let that as energy. And if we want to represent this in an equation, we can see we have plutonium-239 here. And it's obviously 239/94 here. If we look at our periodic table, plutonium is in fact, it's one of the actinides, it's number 94. If it releases an alpha particle, 4/2 helium, 4/2 alpha, it's going to create a uranium-235 nucleus. And we know that this is true because the atomic numbers on each side are going to be balanced. So 94 is going to be the same as 92 plus 2. Top is the same thing. The mass numbers are going to be 239 is the same thing as 235 plus 4. So whenever we write and balance a nuclear equation like this, we must always, always, always make sure that these numbers on the top of both sides of the equation are the same and the numbers on the bottom are the same. That's called conservation of mass and energy. We have to make sure that we obey that, or else physicists from forever ago are going to come up at your door and they're going to scare you. So make sure we balance our numbers here. The second type of decay we're going to look at is really, there's two or three types of it. We're going to be looking at the two of them up here. There's a third one down here, neutron emission and electron capture. They're very similar, but we're going to be looking at chiefly beta and minus and beta plus decay. So in beta minus decay, we have a beta minus particle ejected from the nucleus. So a beta minus particle, we can see here, is the same thing as an electron. 0, -1, E is how we write an electron. We write a beta minus particle is the beta symbol. Don't be afraid of it. Just a B, funny B character. 0, -1. These are the same thing. And we can use either. It's correct if you use either because by the standard model definition, a beta particle is an electron. They've got the same properties here, but we can call it a beta particle because the beta symbol is going to imply that that particle came from the nucleus. So either one is correct. And the other part of beta minus decay is going to be the electron antineutrino. We write that as a nu symbol with a subscript E with a bar over it. And of course 0, 0 for the mass and atomic number. And this is a thing because we have to obey the laws of conservation of mass and energy and momentum and angular momentum and everything. Enrico Fermi actually conjectured that these neutrinos need to exist. They're not important because that does get into particle physics and some more hairy mathematics we're not going to be discussing. But we know whenever we have beta decay plus or minus, there's going to be an electron neutrino or antineutrino that is ejected from the nucleus as well. And then the second type of beta decay is beta plus decay. We get a beta plus particle, which is 0 plus 1, and then our beta symbol, which is the same thing as 0 plus 1 E. That 0 plus 1 E is going to be a positron. The positron is the antimatter counterpart of the electron, and that's what happens when you have beta plus decay. And of course, when you have beta plus decay as well, you're going to get, instead of an electron antineutrino, you're going to get a normal electron neutrino ejected as well. Of course, 0, 0, nu sub E. And then to represent these in an equation, let's say we have this tritium decay here. It's going to release an alpha particle, or not an alpha particle, it's going to turn into a helium-3 nucleus plus a beta minus particle plus an electron anti-neutrino here. This is this representation. And then our beta plus equation, say we have carbon 10 here. That's going to turn to boron 10 plus a positron, a beta plus particle plus an electron neutrino over here. So a cool way to remember these, if you want to remember, beta minus always releases a negatively charged particle. So beta minus will give you an electron. It's minus, so beta minus is minus, it's going to turn into an electron. Beta plus is going to turn into a positive charge, so positron. That's a good way to remember those. And remember, because of laws of conservation, we have to include these neutrinos in here, which are another type of particle in the standard model here. The next thing we're going to look at is gamma emission, and this occurs when a nucleus is unstable. Again, we're going to elaborate on all of these in their own slides, but for now we just need to understand that nucleus is unstable, it's got too much energy, so it's going to release gamma ray photons. Photons are, of course, the quanta of the electromagnetic force, so it's going to be gamma radiation. Radiation on the electromagnetic spectrum, it's going to be in the gamma wavelength. And we denote this with a gamma symbol here, with a 0, 0 for atomic number and mass number. And of course, if we want to write this in equation, because gamma emission deals with metastability, we take our isotope. In this case, it's Rn, so that's going to be radon 222 over 86. When it's gamma emission, make sure we put this M here by the mass number, because that signifies metastability, and the nucleus is going to turn to a normal radon 222 nucleus plus a gamma ray photon emission. Now, the next one we're going to look at is the electron capture, and this is going to release an electron neutrino and an X-ray here. So most of the time we don't write out the neutrinos in any of these equations. I put them here because it's handy to know and because we can see everything worked out here. Most of the time, just know if we don't write it, it's because it's implied that it's there, it's understood that it's there. As far as chemistry goes, in nuclear chemistry, they're not the most important particles, but I put it there because it's a good thing to understand. And so an electron capture is going to be where an unstable nucleus is going to essentially capture a core electron, an electron that's not valence. It's going to be close to the nucleus. It's going to capture it, and it's going to go into one of the nucleons. One of those is going to change. We'll get to quark transmutation in a little bit, and it's going to change the identity of the element. And when that happens, you're going to release an electron neutrino as well as an X-ray photon. So just like the gamma ray photon, this is a photon that's released traveling at a wavelength on the electromagnetic spectrum of the X-rays. That's going to be an X-ray photon. And if we write this in the equation, it's going to be, let's say this Sm here, it's 145 over 62 here. We're going to attach that electron. The nucleus is going to take that electron in, and that's going to turn this into a Pm over 161 element here. So one of these protons got turned into a neutron, and because it absorbed that element, that electron, excuse me, and that's going to release a gamma ray or an X-ray photon and an electron neutrino. Whenever we write this, we must use the electron symbol, because unlike beta minus decay, in this instance, a beta particle is not the same thing as an electron being taken into the nucleus, because the beta symbol is implying that the particle came from the nucleus. This electron symbol is representative of an orbital electron, so it's not from the nucleus. It's taken in by the nucleus, but it's not from the nucleus. So that's very important when we write these. Usually with beta minus decay or beta plus decay, I'll just write the beta symbol. Maybe sometimes I'll write the electron plus or minus symbol, but it is a beta particle. This is not a beta particle. This is an orbital electron that is taken out of the electron cloud by the nucleus, and it turns one of the protons into a neutron through quark transmutation. We'll get to that in a little bit. And then finally, the last one I want to look at is neutron emission. Whenever we do this, this is just when an unstable nucleus it decays and it emits a neutron. So if we have this beryllium-13 here, it's going to turn into beryllium-12, and it's going to release that neutron. And how we denote a neutron is right here. It has no atomic number because it doesn't have a proton. It's got a mass number of 1. We just put N there to denote neutron, and that is the same thing. That's what this is. So again, there are more modes, many more modes, and many more rare modes of decay than these, but these are some of the core ones that I feel like we need to understand. And we're going to do some practice here in a bit. Just make sure we understand what this chart says. We know how to balance these. Make sure the numbers on the top and bottom of both sides of the equation are true. Make sure we know what particles are associated with what. Make sure we know that alpha particle is a 4/2 helium nucleus. Make sure we know that this is an electron, a beta minus particle. Beta plus particle is going to be a positron, antimatter electron, but then electron capture. Remember, we must use an electron symbol. We cannot use a beta symbol there. And we just balance those, and that is how this works. Make sure we know how these work. So we're going to do some practice next. So I'm going to elaborate on each of the modes of the decay that was in that chart on the last slide. So we're just going to go down the chart. So we're going to start here with alpha decay. So let's read what happens. Alpha decay happens when a parent nucleus ejects an alpha particle. Thus, a daughter nucleus and an alpha particle are produced. And that's what this picture down here is showing. So we have our unstable radon nucleus down here, or radium nucleus down here. 226 is going to produce radon 222 and an alpha particle. And this arrow is just showing that alpha, maybe sometimes we can put 4/2 there. We don't have to because it's understood in this context. That means 4/2. I will usually put that there. It's the same thing as a 4/2 helium nucleus. This is really important thing to understand here. And that's all that this picture down here is showing. And then alpha particle is named designated a helium-4 nucleus. Yep, so we understand that already. That's what we said here. And the daughter nucleus produced is going to be more stable than its parent nucleus, but it may still be radioactive. Alpha decay may be the first part or the continuation of a decay chain of a nucleus to a stable state. So we'll look at decay chains in a little bit. All that means is this nucleus is unstable. This nucleus is also unstable, but by comparison, it is slightly more stable than this one because it got rid of that extra mass here. The alpha particle is no longer part of it. So as it turns out, this radon here will continue to decay as part of a decay chain, and this is just one step of it. And that's all we need to understand about alpha decay. So now that we've gone over alpha decay, we're going to be going over the two beta decays that we talked about on the slide with the chart. So obviously, like we talked about, there are two types of beta decay, beta minus decay and beta plus decay. Both describe the emission of a positive or negative beta particle. So if we look at this, this is going to be our negative beta particle. This is going to be the same thing as a beta minus particle, or an electron being emitted from the nucleus. So this makes this beta minus decay. We denote that with the beta symbol with a superscript plus or minus. So this is beta minus decay. Let's make that a bit cleaner. This is beta minus decay. This over here is going to be beta plus decay because this is a positron. It's a positron ejected from the nucleus. So that makes it a 0 + 1 positive beta particle. That would then make this, let's make that a beta symbol, not a B, beta symbol. It's beta plus decay. And these diagrams are called Feynman diagrams. They just show a difference between time and space as time goes forward. It's almost like a visual function. It's a representation of an equation, but we don't need to know how these work. We just need to know that this is the particle exchange that's happening. And in instances where protons are turned into neutrons and vice versa, a quark inside of the nucleon changes from an up quark to a down quark. And this process is called quark transmutation. If we go back to our diagrams here, we see that this in beta minus decay, this neutron is turned into a proton because we have one up quark, two down quarks. If we go up here, there's two up quarks and one down quark. So this makes a proton with a positive charge. This neutron has no charge, it's electrically neutral. And this happens when it's unstable. So right before, one thing I want to point out, right before this beta particle is emitted and our antineutrino up here is emitted, we see that there's this W minus boson over here, and the same thing happens over here. There's these W plus boson. Do you remember what we called these bosons? What do these bosons correspond with? These bosons are the one of the quanta of the weak force, the weak interaction. Weak interaction. The weak interaction is really associated with nuclear decay because it talks about changing one type of particle into another. So this W boson is going to be emitted, It's going to have a very, very short lifespan before it decays into these two. And whenever we have an antiparticle, just a note here, it's going to be facing the opposite direction of time. It's going to be facing toward the vertex, because matter and antimatter has to be created in pairs. So whenever we have antimatter, it's going to be facing the vertex that it came from. And that's just a detail of Feynman diagrams. Let's continue on our slide here. We read the second part. So we learned about quark transmutation. So whenever this beta particle is emitted, one of the quarks here is going to change into either a down quark or an up quark, one or the other. And it's going to change the identity of that nucleus because it'll have one more or one less proton in there. When this happens, a W- or W+ boson is emitted from the nucleus. This is the force carrier of the weak interaction that we did just talk about. And remember, the weak interaction is also called the weak force. Weak force, these are the same thing. Bosons emitted from a transmuted nucleon may have a very short lifespan, and they do have a very short lifespan, after which they decay into a beta- particle or a beta+ particle, and then there are neutrinos up here, neutrino or antineutrino. Another fundamental particle called a lepton, and lepton is just the umbrella term for electrons and neutrinos. And there's some other particles and they're also leptons. And this is just talking about why neutrinos exist. So like we talked about on the other slide, these neutrinos have to be emitted as well because we have to obey the laws of conservation of spin, which is also, remember we don't really talk about this, but this is angular momentum intrinsic to a particle that is not spinning but it has some sort of magnetic momentum and energy. And beta- decaying electron antineutrino, and that's what we see up here. We see the nu. Let's draw that a bit differently. We see the nu, the vinculum above it, and the E. That means anti, the bar above that does. And then a positron emission, we will just see the normal electron neutrino, no vinculum up there. There's nothing up there. And that is just to obey laws of conservation. So beta plus minus decay. There are two types of beta decay. Beta plus decay is sometimes referred to as positron emission. So beta plus, we'll call this, sometimes called to positron emission, but these are the same thing. They are synonymous. Beta minus decay is just a beta particle, an electron being ejected from the nucleus, and this happens because there's a W plus or W minus briefly in exchange there before it decays into those particles. And that is what we need to know about beta decay plus and minus. So now that we've discussed alpha decay and both types of beta decay, we're going to move on to gamma emission and metastability. So let's read what this says. Metastability is a state or property that a physical system can have where there's excess energy in the system that excites it. Nuclei can have metastable states. When a nucleus is metastable, it has extra energy, more energy than it would have normally in a stable state, a non-metastable state, and that causes some instability. To lower its energy, the nucleus will release photons whose wave properties denote them as ionizing gamma rays. Gamma rays can pass through skin and are the most dangerous form of electromagnetic radiation. So let's unpack this for a second. Let's examine this graph over here. So metastability is what's depicted on this graph. So if I label this, we'll already label particle 1, particle 2, particle 3. This is a electric potential graph. We'll call X. We'll call this time, T for time. And this is energy for electric potential. So this is the state of a system as time goes on. There, notice how it's in sort of like a canyon here. It's not way up here with its energy. It's lower in energy than it would be if it was way up here somewhere, but it's not as low as it can get. So there's a barrier preventing it from going up. That's what this little rise and fall here is. But this is the same system. This is state 1, this is state 2, and this is state 3, as labeled by these arrows here. It's the same system even though there's different colors. So in order to overcome this barrier, that system has to lower its energy somehow. And in the instance of a metastable nucleus, and this is metastable, or it's in a metastable state, has metastability applied to it right here. This 1 is metastable. It has to release some sort of energy. And in a nucleus that's metastable, that's going to look like the emission of a gamma photon. Or gamma photons. So remember 0, 0, and then this is just energy. Photon, again, is the quanta of the electromagnetic force, and photons travel with many different wavelengths. The same photons can travel at the wavelength of visible light, at radio waves, microwaves, infrared light, X-rays, ultraviolet, whatever you name it. In this case, metastability in a nucleus is going to lead to emission of gamma rays. Gamma rays are comparatively the most dangerous form of radiation that we're going to talk about today. It's got the shortest wavelength, highest frequency, the highest energy, and it can go through your skin. Some of these particles can and cannot go through your skin. Gamma rays can. They can cause some biological cellular damage. But the important thing to know here is that the gamma emission will not change nuclear structure. So gamma emission, it does not change the nuclear structure of a nucleus or an atom. ST structure. Because all that's happening, notice if we balance an equation with this, the mass number on top and the atomic number on the bottom, they're both 0. So what this is going to be, if we write an unstable nucleus, we have proton number Z and mass number, we'll call this A. We just denote metastability with an M there. And when we balance this, it's just going to be X, A, Z plus 0, 0 gamma photon there. Because nothing changes in the nucleus except for an energy state. There's nothing physical that happens there. We're usually going to see this with nuclear isomers, and that's just a fancy term that means some sort of nucleon has more energy than the rest of them comparatively, and this is really all we need to know about gamma. But the biggest thing to understand is that I can't really draw a circle on that, but gamma emission does not change nuclear structure. All it does is release energy like this. This hill it has to climb over is the release of the photon, and this is the lower energy state that the nucleus will be at once that's done. And that's why we have gamma emission. So now we're going to go over electron capture and neutron emission. I did stick these two on the same slide, but we're going to go over them nonetheless. So in an electron capture, an unstable nucleus is going to effectively capture, aptly named electron capture there, a orbital electron from one of the core electron shells, and it's going to use that to transmute one of the nucleons. So when this happens, we're going to have an up quark inside of one of the protons. It's going to turn into a down quark, and that means that proton is going to turn into a neutron. So if I visually represent this, we'll say state 1 is before anything happens, state 1, and then state 2 is after it. So in state 1 we have 2 up quarks and a down quark. This is a proton. And then state 2, when we get there, we absorb an electron. Remember, we cannot use a beta particle here. We must use the electron symbol for 0, -1e. It's not the same thing as a beta particle because the beta particle implies the particle is ejected from the nucleus, so we don't use that. We must use the electron here. One of these up quarks is going to absorb that electron, and it's going to turn into a down quark. When we have 2 down quarks and 1 up quark, that's going to be a neutron. And in fact, this is going to be exactly what happens in neutron stars because the pressure is so great as it starts to collapse. All the electrons from the atoms are going to be forced into the nucleus. It's going to turn all of the nucleons into neutrons, and then it's just going to compress and compress and compress. We don't really know what happens, but we know that this is a part of what happens in neutron stars. Neutron stars are also a source of electron neutrinos. Not really a source of them, but they emit them a lot. And that's because when we have an electron capture, we're always going to emit an electron neutrino as well, to follow laws of conservation of mass. And then the final thing that's emitted in an electron capture is, of course, a photon. It's not a gamma photon this time. This time it is an X-ray photon. X-ray photon is emitted, again, because we have to follow laws of conservation. X-rays are right up there next to gamma rays. They've got some pretty high energy, pretty high frequency, but not quite as extreme as gamma rays. But that is an electron capture, is when a proton becomes a neutron because an electron from the electron cloud of that atom is sucked into one of those protons and it becomes a neutron through quark transmutation. And in other cases, we're going to move on to neutron emission now. An unstable nucleus can eject one of its neutrons to try and approach more stability. It's called neutron radioactivity, and it is another kind of beta decay. We don't classify it as a beta decay for the purposes of the chart on the other slide to avoid confusion, but on a technicality, it is beta decay. And when an unstable nucleus ejects, it should be CT, ejects a neutron, the atom's identity does not change because only a neutron was ejected. The only difference is it's an isotope. It's a different isotope of the element. So if I have lithium 7, we'll draw the 3 down here. It's going to emit a neutron, 1, 0. It's going to be lithium 6 this time. It's still lithium because there's 3 protons. The number of protons did not change, but there's a neutron ejection, which means it's a heavier, or excuse me, a lighter version of that element, a lighter isotope, but it's still the same element. And this usually is going to happen in a neutron-rich environment, neutron-rich nucleus, and this is why lead is, again, radiation protection lots, especially lead-rich isotope, neutron-rich isotopes of lead are you see this a lot. We'll get to some rare decay modes after this, but this is all we need to know about the electron capture and the neutron emission. So now that we've gone over all of our nuclear and radioactive decay that was on our chart, we're just going to go over some other more rare forms of nuclear radioactive decay that we don't see very often, but we should be informed that they exist because we are talking about interactions in the nucleus. So we just have a list I'm going to read down here. We have internal conversion. We'll talk about that in a second. Single or double proton emission, which is just like our neutron emission we talked about, except it emits a proton or multiple protons, and so the atomic identity is changed along with the mass number. Cluster decay, which is somewhere in between spontaneous fission and alpha emission, alpha decay, is more than an alpha particle but less than another stable nucleus, so we just call that cluster decay. Balanced state beta decay is a bit complicated, so we're not going to go over that one. We're going to skip it for now. Double beta decay, this is referring to beta minus decay most of the time here, just a double beta minus decay here. Double electron capture, we did just talk about that. That's going to be pretty rare. Same with the positron emission. They're both going to be pretty rare in their double forms. We can also see an electron capture with a positron emission. That's usually a special case there. And then an isomeric transition. So we're going to talk about these two here. So for a nuclear isomer, it's going to be describing a state of metastability in a nucleus where one or more nucleons occupy a higher energy level than the normal ground state of the nucleus. And a single nuclear isomer is going to be what this is describing as the higher energy nucleon. This is going to be similar but not the same as how orbital electrons in atoms can get excited when they absorb a photon and jump up those energy levels, their shells here. It's not the same because this is not always referring to a physical quantum jump between energy levels as electrons do in atoms. This is more referring to an energy state of metastability. Not always physical, but the analogy is solid enough, so I added it in there. So it's not the entire nucleus that's metastable. It's not the entire thing. It's just a single nucleon, and that's a unique case. And then internal conversion is the first one on our list up here, so we'll just draw a little star next to this one. An internal conversion is where a metastable nucleus, is going to say, one of these electrons, I don't like you, so it's going to take an electron. Maybe we've got our nucleus here. Say we have an orbital here, this electron. There's 2 electrons here. Maybe we say this is a lithium atom. The nucleus is going to say, I don't like this electron, so it's going to boot it out of the atom. This electron is ejected from the atom. It is not a beta minus particle because it did not come from the nucleus. So this is not a beta minus particle. It's just an electron being emitted, auger electron over here. And as a result of that, we're going to also see a higher level electron up here. So maybe it's in this orbital. It's going to jump down to fill this vacancy. And that's going to cause, because when energy levels are changed in electrons, it's going to release an X-ray photon, so 0 over 0 gamma. That's how we denote a photon here, but this is going to be X-ray this time, because it goes down, it has to conserve that. And this is a thing, this auger electron ejection is the one that's ejected. There is something called auger electron spectroscopy, which is just the observation of the auger effect and things that happen with that. That's a pretty special, unique, specialized field. I'm just going to fix this. This should be an A here. I'm full of filling mistakes today, it looks like. But these are just some more rare modes of nuclear decay that we can see when nucleus is unstable or metastable or anything like that. We're not going to be seeing them in any practice problems. We should be informed that these and more do in fact exist, and we should know that they can happen. But again, we're not going to see those in our practice problems. And that's all we should know about nuclear decay for our nuclear chemistry content. We'll do some practice problems next. So we're going to do some practice problems now. I just have a few nuclear equations written out that we're going to balance, and then we're going to identify the type of decay that's undergoing these. Just as a quick note, I did not include photon emission or neutrino or antineutrino emission in these, so if there's some that's missing, that's all, that's why. We're just going to go ahead and start balancing these then. So remember, whenever we balance a nuclear equation, the numbers on the top have to equal the numbers on, well, the numbers on the top on one side of the equation have to equal the sum of the numbers on the other side. Same with the bottom numbers. So 14, we have a top number of 14 on this side for a mass number. We have 0 over here for a beta minus particle. So we know this top one has to be 14 over here. That's weird, okay. 14. And we have 6 over here. We have a negative 1 over here. How do we balance this? Well, this is going to be 7. And if we look at our periodic table, we're going to see that element number 7 is in fact nitrogen. And if we classify this, this is going to be, let's do it this way, this is going to be beta minus decay. Let's move on to this one. Let's balance it the same way like we did up here. So it's going to be 13. So we have 1 over here. We have to put a 12 to balance that. And then we have a 4 and a 0. So this has to be 4. This is going to be, element number 4 is beryllium, and this is going to be a neutron emission. Now over here, we have to balance this one, except this time we're only given the products. So our mass numbers, let's balance those first. It's 6. Let's balance our numbers down here at the bottom. That's going to be 6. 6 elements on the periodic table is in fact carbon. And this is a positron. This is the same thing as a 0 plus 1 positron. Therefore, this is beta plus decay. Moving on to this one, we have a 235 over here, and we have 231 over here. So if we balance our top numbers, it's going to be 4. If we balance our bottom numbers, we have to have a 2 here. And our second element is helium. We can also write this as 4 over 2 alpha, because that's what an alpha particle is. Or if we really wanted to, we could just write alpha there. I'm going to include the 4 over 2 just to make sure we understand what that is. It's an alpha particle. So anytime we have an alpha particle, it's going to be fission. More specifically, it's going to be alpha decay or alpha emission. Then our last example over here, we just have a 200 on the left side on the top and a 200 on the right side on the top. So that has to be 0. And then we have an 84 on the bottom on the left, and 83 on the bottom on the right. We have to put a negative 1 here. So we have this. This is not correct. We cannot do this, because anytime we have an electron on the left side, that is an electron capture. This, in this case, is not the same thing as an electron. So we can't use the beta particle notation. We have to use the electron here. And because the electron is on the left side, this nucleus is capturing that electron. So this makes this an electron capture. Let's make that a bit cleaner. Electron capture. So let's recap this. So over here, we have a beta particle being emitted. So this is beta minus decay. We have an electron, a negative beta particle. So this is beta minus decay. And all we did here is balance the numbers. Same thing down here, except it's a beta plus decay. We have a positron emission here, also called beta decay. Beta plus decay is also called positron emission. Remember, we just balance the numbers here. This is a neutron emission. It's an example of fission on a technicality because there's a parent and a daughter nucleus here. We just balance the numbers. This is all we get. The element here did not change. This is still element 4, beryllium. There's still 4 protons, but we do see a neutron ejection. So we have to take the mass number down by 1. So it's just a different isotope of beryllium. It's become beryllium-12 instead of beryllium-13. Over here we have alpha decay. We have uranium-235 decaying into thorium-231, and that is by alpha decay. So we have a helium-4 nucleus being ejected here, or the alpha particle. Again, with just Greek letter A for alpha. And that is alpha decay. And then for electron capture down here, remember, like we talked about, we have to use the electron symbol up here. We can't use the beta symbol, 0, -1. We just balance our equations. And one of the protons in this polonium atom is going to become a neutron, excuse me. So the mass number is going to stay the same. That doesn't change. But there's going to be one less proton, and so that's going to become, instead of polonium, that's going to become bismuth. Bismuth 200. And that's our electron capture. These are our practice problems here. So now that we've learned about how individual nuclear decays work and their properties and how those work on a conceptual level, we're going to be looking at decay chains. So let's read what the slide says. Even after undergoing nuclear decay once, a nucleus may still be unstable, which we've talked about, whether because it is metastable, because it has extra energy, or its nucleon ratio is not in the stable region on the band of stability. And remember, that just maps out proton versus neutron numbers in a ratio. Nuclei that remain unstable after decaying once will remain radioactive. They will remain unstable until they achieve stability, meaning that they will continue to decay until they get there. A series of nuclear decays that an unstable nucleus undergoes is called its decay chain, and decay chains will often reflect mixed modes of decay. And these are examples of decay chains. So if we look at these, we're going to see that maybe an element, in this case radioactive uranium, up here it's radioactive thorium. They're going to undergo various types of decays to get down to a stable isotope, and we'll talk about this in a second. But a lot of the stable isotopes for heavier elements, they're going to land on lead after decaying. And we can see these little emission markers here, mixed modes of decay. This one, thorium, alpha, beta minus, alpha, 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 beta minus. Then it goes beta minus or alpha, then beta minus to alpha, and then it'll do a lead. Most decay chains are either beta minus or alpha decay. Sometimes you'll get some metastability, gamma emissions in there, maybe even some electron captures. Those are going to be rare. Most decay chains are going to be alpha and beta minus decay. And they're not just one or the other. They're going to be dispersed through there with multiple modes. And because lead, remember lead is Pb, lead is going to be number 82 on the periodic table, is the last element before every isotope of every element past it is intrinsically radioactive. Many heavy elements, decay chains, and an isotope of lead, which we do see here. Like on this one especially, uranium is going to decay a whole bunch. Down here it's going to get into this almost spiderweb looking thing. Lead is on here a couple different times, but then the final instance, everything is going to lead to this lead isotope, and I believe, I can't quite read it from here, it's a little bit blurry, but I believe that's lead 206. This is lead 208 over here. So lead for especially heavier elements is going to be a good endpoint, because it's got those neutron-rich environment, but it's got a good stable ratio between its protons and neutrons. And just a little fun fact here, tin, which is Sn on the periodic table, has the most stable isotopes out of every element. We're going to do some practice problems with these in a second to make sure we understand this. So we're just going to do a quick practice problem here to make sure we understand the concept of a decay chain. So let's read the question. It says Neptunium-237 decays into Thallium-205. The following is the progression. And we have a list of alpha and beta decays. Anytime it says beta decay, we're going to assume beta minus decay for these in order to make this work. And it says to write 3 steps in the decay series. We might do more just to illustrate the concept. We're going to do at least 3. So we start off with Neptunium-237, so let's go ahead and write that out. Mass number is 237, remember the element name and then the mass numbers right here. Neptunium is going to be Np, and it is number 93 on the periodic table. So the first decay is alpha decay, so we'll draw our numbers in. What do we get? 233, 91, 91 is going to be Pa. So this is our first decayed into nucleus right here. If we draw an arrow over here, I'm not going to draw an arrow, we're just going to start over here new. 233, 91. We take the last element, we just draw it here again. A. We did alpha here. We're going to do beta minus decay. We can use the electron or the beta minus symbol here. I'm going to do the beta minus symbol to imply that the particle does come from the nucleus. So if we balance this, it's going to be uranium-233. This is the second step here. This is the second part of the decay chain. The second nucleus it decays into is what we're looking at here. So if I go 1, 2, 3, 233, 92, uranium, and it wants alpha decay again. So we're going to do, put our numbers in to help us visualize. Don't have to, but it helps. So if we do this, it's going to be 229 and 90, and this is going to be an isotope of thorium, because thorium is, of course, element 90 on the periodic table. And these are our 3 steps, and if we wanted to, we would just, if we want to do the 4th one, we could just do 229, 90, thorium. This is alpha decay again, 4/2 alpha plus whatever, and we would continue this until we got to the final isotope. But we're not asked to do that, we're asked to do just the first 3 steps, and this is how we do that. So remember, we take whatever step in the decay chain we're given. It'll give us a method or a mode of decay. We take whatever we started with, or the last element, we decay it that way, and whatever we get is whatever our resulting isotope is we start with on our next step. So this is just decay chain practice, really simple, straightforward concept just to make sure we got it. So now we're going to move on to the last sort of bit of content we're going to talk about for nuclear chemistry, and that's going to be the concept of half-life. Probably the most important concept in nuclear chemistry that we've talked about today. So let's read what it says. Unstable nuclei do not undergo decay at the same rate. A sample of one unstable isotope of an element may decay at a much quicker rate than a sample of another isotope of the same element. To quantify this, chemists and physicists as well use half-life. Half-life is a measure of the amount of time that passes in order for half of a given sample of an isotope to decay into something else. As a function of time, the equation for half-life is given down here. So we have the amount of the sample left after a given amount of time, A of t. We have the initial amount, A sub naught, multiplied by 1/2. And then in the exponent, we have the time elapsed on the top, just as t. And we have that over the half-life, which is abbreviated here as t sub 1/2. And those time units can be whatever as long as they match for good. Usually, this is going to be, the amounts are going to be measured in grams because that is the SI unit for mass. But this is the equation for half-life. It is not this half-life, don't get the wrong impression. But half-life, if we were to graph it, would look something like this. If we were to graph this for a group of isotopes. And just an important distinction here, decay modes are the mechanism by which unstable nuclei achieve stability. Half-life is the quantification of time it takes to accomplish each step to get there. So half-life is not a decay mode itself. Half-life is just a measure of time for an element, for half of a sample of a radioactive isotope to decay into something else. Half-life itself, again, is not the decay mode. It's not the mechanism. It's just the measurement of time for half of that mechanism, if you so to speak, it takes to happen. Now, up here where it says one isotope of an element has a much shorter or longer half-life of another one, take carbon. Carbon-12 is extremely prominent everywhere, you know. Carbon-12 has a very long half-life. Bismuth. Some isotopes of bismuth have half-lives longer than the lifetime of the universe. Some other elements will have half-lives in seconds or minutes. It really depends on the element and the nuclear arrangement. Remember, the band of stability determines that stable ratio between nucleons, between neutrons and protons, and the farther it is away from that, generally speaking, unless it's metastable, it's going to have a shorter half-life. Now, when you have metastability in a nucleus, it's going to have a drastically longer half-life than something that's not metastable. But I digress. This is the important equation we need to understand, and I'll erase this just so we can get it. Memorize this if it has not been memorized, because we're going to do some practice next, and this is a really important model to understand when it comes to nuclear chemistry. Alright, so we're just going to do 2 quick practice problems here to make sure we understand the concept of half-life. The first question reads, the half-life of a fictitious isotope is 5.43 minutes. So we understand this is a radioactive isotope. There's a sample of 25.0 grams of the isotope exactly. How much of the isotope remains after 20 minutes? So our half-life equation is A of t is equal to A naught multiplied by 1/2 times the elapsed time over the half-life. So we can use our half-life equation directly if we substitute what we know. So we're looking for A of 20 equals 25.0 grams to begin with, so A naught there, the initial amount, by 1/2, make sure we include the 1/2 in there. The elapsed time is going to be 20 minutes, and the half-life is 5.43 minutes. Now if we put this into our calculator, we're going to get, let's look at significant figures first. So we have 2 here, we have 3 here, we have 3 here. So we're going to use 2 significant figures. That's going to be approximately 1.9 grams. We measure that in grams. So that's the half-life for this one. Or that's the amount left after 20 minutes given the half-life for this one. The second question reads, let's clear my calculator. If 1/8 of the original sample of Krypton 74 remains unchanged after 34.5 minutes, what is the half-life of Krypton 74? So the initial sample started as 15 grams. How much would be left after the hour? So this is a 2-part question. So we're going to ignore the second part right now. I'm going to go ahead and ignore the second part for now. We'll get that when we get to it. So if 1/8 of the original sample of Krypton 74 remains unchanged, so what does that mean? So we have 1/8 of the original sample. So that remains unchanged. So we're going to do 1/8 of x. We use our equation. We're going to do 1/8 a sub naught equal to a sub naught 1/2. It remains unchanged after 34.5 minutes. So we don't know the half-life. That's what we're looking for. We know the elapsed time. It's going to be 34.5 over x. So if we divide by, these are going to cancel out. We don't need this. Those are both terms inside the equation we don't need. So we can get rid of that. So it's going to be 1/8 equals 1/2 to the 34.5 over x. So if we put this in our calculator, it's just going to be 1/8, of course, equals 1/2 to the, what was it, 34.5 over x. The half-life, x, why don't we change this to t sub 1/2, just to keep notation consistent. So the half-life, if we solve this, is going to be equal to, let's see, we got 3 significant figures. We have 3 significant figures. We're going to do 3 significant figures here. 11.5 minutes. And this is the first part of the question. So we know the half-life is 11.5 minutes. Now what about the second part of the question? The sample started at 15 grams, so this is another scenario here. Let's make sure, let's write this over here. So these are 1/2 equal to 11.5 minutes. So we're going to have to erase this. So we're going to use our equation more directly this time. And we can solve this with algebra, no calculus needed. There is a calculus derivation of this equation, but that's a little bit more than what we need to worry about. So if the sample started as 15 grams, how many remain after an hour? So we know the half-life, we know how it started as, and we know the elapsed time. So let's use our equation more directly. So because the half-life is in minutes, we're going to turn this into 60 minutes. This is of Krypton 74. So A of 60, I'm just going to draw an arrow down here. We're using the same equation here. A of 60 is equal to the initial amount, 15.0, times 1/2. The elapsed time is going to be 60 minutes over 11.5. So if we solve this in our calculator, remember this is just x or y or whatever. Solve this in our calculator. X is going to be equal to 15.0 times 1/2 times the elapsed time, which is 60. Nope. elapsed time, which is 60 minutes over the half-life, which is about 11.5 minutes. Now, after an hour, there's going to be, we use three significant figures, 0.403 grams of krypton 74 here. We should label this one as well, so we'll just label this as element X. And this is the answer to our second part of the question. And we did solve for our half-life up here, so there's the first part of our question. So this is our half-life review. For this one, we just canceled terms that we didn't know, and we solved for the half-life. This one, we just substituted that in, along with everything else we know. Up here, we just used our equation directly, and that's our review for the half-life practice. We're going to move on to some section review after this. So for the first part of our review today, we're going to be going over everything we've done so far, everything we've reviewed. For the first part, we're going to be going over average atomic mass. So the question reads, mass spectrometry data for a sample of an element is collected and organized into the below chart. Using the data, compute the average atomic mass and identify the element. Then represent each of the isotopes shown in standard nuclear notation. So this kind of goes over a couple different things. But at the heart of it, we're going to be using average atomic mass. So remember our formula for average atomic mass is going to equal the mass of isotope 1 times the abundance of 1 relative abundance plus the mass of isotope 2 relative abundance of 2 plus ... for all of them. In this case, we get to do that 5 times. 5 times, not just 4 or 5. So why don't we expand this? So the mass of isotope 1, let's call this, again, average mass is going to be 191.961 times 0.78%. So remember, to get a relative abundance 0.78, we divided that by 100. It's going to be 0.0078. 0.0078. That's our first term down. Let's cross that one off. The next one is going to be 193.9627. multiplied by 0.3297, or relative percent abundance. Second one done. Our third isotope is 194.969648 times 0.3383 plus, what's the third one done? Fourth one is going to be 195.965, nope. 95.965, and there would be a 0 there, times 0.2524 plus 197.0678 times 0.0716. So if we put this in our calculator, put this into our calculator, 191.961 times 0.0078 plus 193.9627 times 0.3297 plus 194.9648 times 0.3383 plus 195.965 times 0.2524 plus, it's a bit of a long one, isn't it? 197.0678 times 0.0716. We get our average atomic mass to be just about, we're going to round a little bit here, 194.98 AMU. So if we look, if we draw a circle around this, an actual circle, you know, like this. Okay, if you look at our periodic table, what element is closest to this average atomic mass? And the answer is platinum. Platinum is element number 78, so that means that the element in question is platinum. So we have our average atomic mass calculated. We know the identity of the element. So now we're going to write I'm going to write the nuclear standard nuclear notation of all the isotopes. So we have 5 isotopes we need to look at here. So I'm going to go ahead and erase these cross out marks just to know we haven't done that part yet. So our first isotope, remember we round this to the nearest whole number. So isotope 1 is going to be platinum 192. Isotope 2 is going to be platinum 194. Isotope 3 is going to be platinum 195. 95. Isotope 4 is going to be 196, platinum 196. And isotope 5 is going to be platinum 197. And of course platinum is the 78th element, so if we really wanted to be specific we could do 78 down here. It's understood that that is there because we do identify platinum with a symbol, but we can't include 78 there. So I'm going to go ahead and draw a square around these ones, fancy square here, and that is this practice problem answered. So what did we do here? We took the given data from the chart obtained from and organized from mass spectrometry. We computed the average atomic mass, we identified the element that's in the sample, and then we identified all the isotopes. So that is our average atomic mass question. Alright, so now we're going to be reviewing just some vocabulary to make sure we understand nuclear structure and subnuclear structure. And so we got some questions, we're just going to write out the answer below them or to the side of them. So the first one asks, the proton and neutron are states of what? What is the structure of these objects called? So protons and neutrons are states of the nucleon. So who wants to write? Maybe? Nucleon. What is the structure of these objects called? The structure of these objects is called a nuclide. So the atomic nucleus is an example of a nuclide. What force binds the nucleus together? What is this force the derivative of, so to speak? The force that binds the nucleus together is the strong nuclear force. Strong nuclear force is, in a way, the derivative of the strong force, the strong interaction. We know that the strong nuclear force refers to the nucleus because it has nuclear in the name. And nuclear describes in relationship to the nucleus. So the strong nuclear force is the, quote, leftover of the strong force, and that's what holds the nucleus together. What is a hadron? What are two excellent examples of hadrons, or hadrons, or however you say it, however you'd like to say it? A hadron is two or more quarks bound together by the strong force. Quarks will say strongly bound. Two excellent examples of hadrons are protons and neutrons. Because they are three quarks, they're up and down quarks with a 2 to 1 or 1 to 2 ratio between the two. And by definition, those are hadrons. What is a fermion? What is a boson? A fermion is a fundamental matter particle. Fermions will always have a spin within 1 of the spin magnitude, which is 1/2. So it's either going to be 3/2 or -1/2. A half integer spin, essentially. So fermion is a fundamental matter particle. What is a boson? A boson is a force-carrying particle, so they're not physical. Fermions are physical matter particles that make up matter. Boson are force-carrier particles. They represent forces, so they're not physical. Force-carrying particles. Bosons will always have a spin of 1. Well, vector / gauge bosons are synonymous. They'll always have a spin of 1, an integer spin. What is a quark, and how many quark types and antiquark types are there in total? So a quark is one of the fundamental fermions. There are 6 types of quarks. There are 12 types of quarks total if we include antiquarks in there. So a quark is half of the fermions, is 1/2 of the fermions. It's a classification. Of fermions. There are 12 different types of quarks if we include normal quarks and antiquarks. We're just going to do normal quarks plus antiquarks. Again, that bar, that vinculum, just means antiquark. So if we read from left to right, the first generation of quarks is going to be up and down quarks. Second generation of quarks is going to be charm and strange quarks. And then the third generation is going to be top and bottom quarks. Top quark is the heaviest out of all of them. What is the gluon? What force do gluons mediate? The gluon is the gauge boson of the strong force, and it would mediate the strong force. Quanta of the strong force, or strong interaction. See it both ways. It's a vector boson, a gauge boson, those mean the same thing. So again, an integer spin. What force chiefly describes interquark dynamics? And this is going to be the strong force, again, the strong interaction. And the study of this is called quantum chromodynamics. Chromo meaning color, that is the symmetry in the strong force. When describing it, we abbreviate that as QCD. Studies this. What force is mediated by pion exchange between nucleons? So remember, between quarks we have gluons being exchanged. That's how that works. Between nucleons we have pion exchange. And between nucleons, well, nucleons make up the nucleus, so this must be the strong nuclear force. This is because, again, nuclear refers to the nucleus. That's how we know it's talking about the nucleus. Nucleons gives us it's in the nucleus, and pion exchange is, of course, what's exchanged between nucleons. And the next question is sort of a follow-up here. What is the repulsive force between nucleons that the nucleus overcomes by staying together? It's going to be the electromagnetic force. Electromagnetic force, one of the four fundamental forces. Because like charges are going to repel, opposite charges are going to attract. So, by Coulomb's law, a positive and a neutral charge should not attract, but the strong nuclear force overcomes that and says, yes, we're going to stay together. And that's how the nucleus is, a structure that stays together. Last question here is, what force is associated with radioactive decay? What particles mediate it? Are they fermions or bosons? So the answer to this one, the first part, is going to be the weak force, or the weak interaction. Of course, the weak force is more than just radioactive decay, but for our purposes in looking at nuclear chemistry, we just need to need to make that association that the weak force, or the weak interaction, is beta plus and beta minus decay with that exchange of its mediating particles, which in this case are the W plus and W minus bosons. The weak force, we'll draw an arrow. Mediated by W plus and minus bosons. Weak force is also mediated by Z boson, which is neutral, but that's not part of nuclear chemistry, so we don't worry about that for the stuff we covered. But we just need to know that that's in there as well in case we do see it, if we were to. And then these are going to be bosons, because they are force-carrying particles. They are the vector or gauge bosons of the weak force, because they represent the weak force. The weak force isn't a particle. The weak force is a term described or descriptive of exchange of W plus and minus and Z bosons. So that's our vocabulary review for nuclear and subnuclear structure. So now we've got some reviews for our nuclear equations. Make sure we understand nuclear decay on a singular basis. We've got 6 questions here. And it says to include all particles and the ones where it's necessary. So that means we're going to include all the neutrinos, antineutrinos, gamma rays, X-rays, whatever it might be. So we're going to go ahead and start with the first one, the electron capture of potassium-40. So we know the mass number is, of course, 40. Potassium is the 19th element. K plus an electron capture. Remember, we have to use the electron symbol because it's not coming from the nucleus. We're going to get argon 40, because element number 18 is argon, so Ar, plus an electron neutrino, plus an X-ray. We're just going to know that like this. We'll say X-ray after that. There's that one, electron capture of potassium 40. Write an equation for the alpha decay of polonium 210. Include all particles. So polonium, we know it's 210. polonium is number 84 on the periodic table, PO. We're saying it's an alpha decay, so we're going to use the alpha symbol. We could also do this. We could, but we're going to go ahead and use the alpha symbol because that is more appropriate. Alpha decay of polonium 210. And we're going to go 206 for 82. That's going to be lead, Pb. There's no other particles, so we're done with that. Write an equation for the beta plus decay of proactinium 230. Include all particles. So proactinium, if we look on the periodic table, that's Pa, that's element 91. Be 230, 91, 91, not 90. Proactinium. The beta plus decay, so that means it's a positron emission. So we're going to go 0, positive 1. We're going to use the beta particle. We can use the electron or the positron there if we wanted to, but we're going to go ahead and use the beta particle. Proactinium plus the 90, so it's going to turn to 230. And element 90, if we look on the periodic table, is just thorium. And we have to include an electron neutrino. There we go. Write the equation for the gamma decay of technetium 99. Include all particles. So if we look on the periodic table, technetium is element number 43. It's 99 over 43 is going to be Tc. Yep, Tc. And it says the gamma decay. So remember, whenever we have gamma decay, we have to mark metastability up here. So we put an M next to the mass number. And then, of course, the nuclear structure is unchanged. And then we do a gamma photon there, and we say gamma. Remember, that's ionizing radiation of that photon. And last one, second to last one, says write the equation for the beta minus decay of cobalt 60. So cobalt on the periodic table is CO, and if we look for its number, it's going to be number 27. 60 over 27 CO. It says beta minus decay, so that means we're going to get an electron being released, so 0, negative 1. I could do this. I'm going to use the beta symbol to simplify it's coming from the nucleus, or to show it's coming from the nucleus. I'm going to add that this has to be 28 over 60, and the element right next to cobalt is going to be nickel, so Ni for 28, and then we have to add an electron antineutrino, so 0, 0, V with a vinculum over it. And that is that one. So now we have a little bit of a challenge problem, although it's not much of a challenge. It says complete the following equation for the neutron emission of uranium-235 after its fission. So for this one, we just have to fill in the blanks. So we know that we're starting with uranium-235. If we look on the periodic table, uranium is element number 92. We put a U there. That's the left side done. Let's fill in what we know over here. So 94 over 36. What's element number 36? Element number 36 is krypton, Kr. So 94, 139 plus 94 plus 2, we have to multiply this in our equation, plus 2 times 1 is going to give us 235. So we know the mass numbers are balanced. So this must be a neutron, and we know that there's a neutron emission. We just have to put that there. So then what's the deficit here? We have to figure out the atomic number for this isotope over here. So the top is balanced. We're going to look at the bottom now. So what's 92 minus 36? 92 minus 36 is going to be 56. So if we look on the periodic table, element 56 is going to be barium. So now if we double check to make sure we balanced everything, 235 is equal to 139 plus 94 plus 2 times 1, or just 2. The top is balanced. 92 is equal to 56 plus 36 plus 0. We get 92. So this is our balanced nuclear equation for uranium-235 neutron emission after it's fissioned. So this is our review for singular nuclear equations. Make sure we understand this. We'll all be good. We're going to move on to decay chain review next. Alright, so now we've got a decay chain practice. Now let's read what it says. Complete the decay chain of uranium-233 using the transitional information provided. In each box, indicate the resulting isotope using the correct elemental symbol, mass number, and atomic number in standard nuclear notation. Remember, all standard nuclear notation is just for some element X. We have the proton number Z and the mass number M. That's all that is. and there should be an L here. I guess I got cut off by this image here, but let's remember how we do this. So we take whatever we're given and we do whatever decay mode it gives us. And we got some divergence down here in our decay chain. That's okay, we should end on the same isotope of the same element. Let's get started here. So we're started with uranium, 233. 233, 92, uranium. It says do alpha decay, so we're going to do 4 over 2, alpha particle, plus 233 minus 4. 233 minus 4 is, of course, 29. 229. 90, and that is going to be thorium. So 229 over 90 thorium. We got rid of the alpha decay, so we're going to move on now. So 229 over 90 thorium. It says another alpha decay. Okay, 4 over 2 alpha plus 229. 229 minus 4. We get 225. 225. 88 on the periodic table, element number 88 is going to be radium. Second alpha decay done. 225, 88, Ra. Could have made these boxes a bit bigger, but it's okay. So now we have a beta minus decay. Okay, put in something different in here. So beta minus decay, we're going to start obviously with what we did last time. So 225, 88, Ra. Do a beta particle, do beta particle notation this time, plus 89 over 225, and then element number 89 is going to be AC. 225, 89, AC. There's that one. We're going to go ahead and erase these. So we did the first few decays, so we get the idea of how a decay chain works. So I'm going to go ahead and plot through the rest of these as it gives me. So 225, 89, AC, alpha particle, so 4 over 2 alpha, 221, 87, 87 is going to be francium. 221 plus 4 is 225, so it's going to be 221, 87. Francium is in fact the biggest element, the largest element in the periodic table, in its non-ionized form. So we did the alpha decay, another alpha decay, 221, 87, Fr goes alpha decay again, lots of alpha decays here, 2 plus 221 minus 4, going to be 217, 87 minus 2 is 85, on the periodic table number 85 is going to be AT, so we'll put that over here, 217, 85, AT, continue, 85, AT, okay, so we want another alpha decay, 4 over 2 alpha, it's going to be 213, 83, number 83 on the periodic table is bismuth. Bismuth, we're getting close to lead, you know, that stable element, 213, 83, bismuth. We're going to go this way. I'm going to go ahead and do this across over here. So 213, 83, bismuth. We want a beta minus decay, okay. 0, -1, beta particle, plus 84, 213. Number 84 on the periodic table is going to be polonium. 213, 84, polonium. And then we want another alpha decay after that. Let's go ahead and erase all of this. Alpha decay, 213, polonium. Alpha is going to be 213 minus 4. 213 minus 4 is just going to be 209. It's going to be 82, and lead is number 82 if we look on the periodic table. So 209, 82, Pb. So let's go ahead and do these last two decays. So we have another alpha decay of bismuth 213, 213, 83, bismuth. It's going to do an alpha decay. So we've already done this, going to cross this through to alpha decay. 213 minus 4 is just 209, is 81. Down here, 81 is going to be TL. 209, 81, TL. There's the alpha decay done right there. And if we do a beta decay here, we should get the exact same thing, lead 209. So 209, 81, TL, 0, -1, beta, plus 82, 209, and that is in fact lead 209. So this is our final particle. This is where we get our stable isotope here. So if we erase all this and just go ahead and look at our table, what do we see? Does this make sense? So we saw a divergence in decays from bismuth 213. It can either go another beta minus decay, then an alpha decay, or another alpha decay, and then another beta minus decay. But in the end, we do in fact reach that lead 209 isotope. That's our stable isotope at the end of the decay chain. Does this make sense? Yes, it does, because remember, every element, or rather every isotope of every element past lead, past 82 on the periodic table, is intrinsically radioactive by nature. This makes sense. Lead is very neutron rich here. It's got 209 in its mass number, 82 protons. So how many neutrons are in there? There are 127 neutrons in this isotope of lead, and it's going to be stable. So seeing as uranium and most of the elements on here, in fact all of them are heavier elements, they're going to decay into lead 209. That makes sense. So now we're on to our final slide of review, and these are 3 half-life questions. So before we do anything, I'm going to write out the half-life formula up here. So A of t, as a function of time, half-life is going to be this. This is a function of time here. So we're going to write this down, not forget this. Maybe we can use this directly in these, I don't know. Let's give it a shot. The first question says, after 45.0 minutes, I have 12.3 grams of a sample of a radioactive isotope, and I started with 33.4 grams. What is the half-life of the isotope? So it's know it's radioactive. We can use our equation directly here. So we know the elapsed time, we know the grams that we have, the grams that we started with. So we're looking for the half-life here. We have 3 of the 4 variables, we can solve it directly. So A of t, we already have that. So we don't need to do any A of t things. So we have 12.3 equals the initial amount, 33.4, times the 1/2 times the elapsed time is 45.0 over t sub 1/2. So if we put this in our calculator, what are we going to see? We're going to see 12.3 equals 33.4 times 1/2 times 45.0 over x. If we solve for this, we're going to see that the half-life is equal, how many sig figs? We have 3, 3, and 3. So we have 3 sig figs here. So we're going to do 31.2 minutes as our half-life. So our answer for the first question is 31.2 minutes. Alright, what about the second question? Let's go ahead and clear our calculator. Let's read it. The half-life of gold 195 is 186 days. How many grams of gold 195 do I have after 2 years if I start with a sample of 50 kilograms? Okay, so we're looking for it after an amount of time. Say after 2 years. We got to do a conversion here. So the half-life is given in days. We have 2 years. So 2 years, if there's 365 days per year, there's a little bit over 365 per year because time changed. 365 times 2 is going to be 730 days. So we have to keep everything in days here, or we could turn it to years. We're going to go ahead and do days for the sake of simplicity. So A of 730 days is going to be the initial amount, 50 kilograms. Oh, we got to do another conversion here. So the SI unit for mass is grams. We have to convert 50 kilograms to grams. So if we go ahead and do that, do a unit converter. So 50.0 grams, 50.0 grams, kilograms, is going to be 5 times 10 to the 4th grams. 5 times 10 to the 4th is going to equal 50,000. That's a lot of grams. So we're going to say 50,000 grams times 1/2 times the elapsed time, 730 days we said, over the half-life is 186 days. So if we go ahead and solve this, A of 730. Put this in our calculator. X is going to equal 50,000. That's a lot. 50,000 grams. I guess we're in an industrial shipment here. Times 1/2 times power of 730 for 186. 186. If I do this, I'm going to have 3,000. We have 3 sig figs. Okay, so 3,290. 3,290 grams of gold, 195. We could turn this into kilograms if we want, but for SI unit sake, we're going to keep that in grams. That is how we'd solve this one. What about the last question? Okay. The last question reads, how many grams of a fictitious radioisotope did I start with if now, after 1 day, I have 12.8 grams? The half-life of the isotope is 1.43 hours. So we get to do a little bit of a conversion now here. Because the half-life is given in hours, we're going to turn 1 day to 24 hours. Alright, how many grams of fictitious isotopes? So we're looking for the amount of time of something. So we're going to say A of 24, because 24 hours equals, oh, never mind. So we're going to look, we already know how much of that. We're going to 12.8 equal to A sub naught 1/2. The elapsed time is going to be 24 over 1.43. To put this in our calculator, 12.8 times x is 1/2 times 24 to the power of 24 over 1.43 hours. So we're going to have a lot of this stuff. Wow, okay, so A sub 0. How many sig figs? 3 sig figs. Okay, so it's going to be, wow, that's a lot. 1, 4, 4, 0, 0, 0, 0. That is quite a lot. Grams of isotope X. We'll just do this. I'll draw a square on this one. So this is our final half-life question solved. This is how many grams we would have, and it makes sense, right? Now check if the other ones make sense as well. So what do we see in these other ones? This last one, we have a really short half-life, and it's after 24 hours. We know how many we have at the end. So this makes sense. This large number makes sense right here. Does this one make sense? It does, because we started with 50 kilograms. We know the half-life, and we're asking after 2 years. This does make sense. This one also makes sense, because we're solving for the half-life, and it mathematically has to. So that is all for the nuclear chemistry review. We've gone over what atomic structure, nuclear and subnuclear structure, decay chains, nuclear reactions, half-life, average atomic mass. We've gone over a lot, and these are skills that are really important in nuclear chemistry. So hopefully this is helpful. These review questions, feel free to go and do them over, see if you did it right, and I'll catch you next time.